afternoon, everyone. Lovely to see you all again. Yesterday, we went from a simple set of assumptions from a working sketch of a linear pattern search using finite state automata as a tool to help us understand this linear pattern search algorithm. Today, we're going to revisit yesterday's algorithms and give you a few different intuitions that you can use to help build up your comfort. Linear pattern search ran in O of mn time by performing a comparison against every letter of the pattern for every letter of the target string. We looked at one possible improvement to the algorithm that allowed us to skip over some of this work. We began to investigate the KMP algorithm, which was our new improved version of linear pattern search, and one way of doing this skipping process that allowed us to, again, improve on the efficiency. Let's take a pattern that contains only unique characters. That is, no character is repeated within the pattern that we're looking at. If you look at this pattern here, you'll notice that the letter A appears only once in the string, the letter B only appears once in the string, so on and so forth. We can combine this with a few facts about our overall process in order to build intuitions that allow us to do this skipping. So let's say that we are looking at a location K in the target string. If the match starts at K, then T of K has to equal pattern 0, because that's how we know we're at the start of a match. That's our first fact here. We also know, this is our second fact, and these both seem trivial, but don't worry, they'll be used together in a second. The character at pattern 0, that is the first character in the pattern, doesn't appear anywhere else in the pattern. And we know this because we just said a second ago that we're considering a special pattern that only has unique characters in it. The implication of this is that if we find a mismatch at some location in the target string, we can skip I characters in the target string and we don't have to do what we did in linear search, that was comparing each of the characters over and over again from the start. No duplicates in our pattern means if we've already compared I characters and we're looking at the I plus 1th character, then we can go ahead, if we detect a mismatch, and move the location at which we expect to find a pattern I characters along. So again, if we're looking at the I plus 1th character and we've already matched the other I characters, because there are no duplicates in our pattern string, we know that A matched with A, B matched with B, C matched with C, and now we get a mismatch with D or so. But we know that there's no other A in the section that we've visited so far, so there's no other place where the pattern could have possibly begun that we've already looked at, allowing us to do this skip. Here is an example of one such target string and pattern that matches this scenario. Here we have a pattern that has all different letters, and we have just a sample target string to work off. So consider A, B, C, D, E, and the target string A, B, C, D, A, B, C, D, E. Our first set of comparisons starts at index 0 in the target string. So that's at that very first index there. And we're going to progress C along from C and compare it all the way along there, with their grouped together. Let's ungroup them for a moment, and then we can check at which location our pattern begins. So I will ungroup these. If S is over there, we're comparing C with S plus C. C is 0 at the time being, and we have a match. Let's move along. S plus C moves up 1 because C moved up 1. Compare B with B, matches. C with C, D with D, matches. D with E doesn't match anymore. Now, we know that in order for any of these positions S to match, there must be an A there. And we also know that the only A that we've seen thus far is that first A over here, because we already stipulated that our pattern only contains A once. So we know if we've detected a mismatch, we can shift our S all the way along to after the mismatch, and then move our pattern along, and start again. So now A with A, B with B, C with C, D with D, E with E. This gives us a sense of what a more basic KMP algorithm looks like, one that only works if there are no repeats in our pattern. Here I have the same pattern, only now I've built our transition table. And in our transition table, there's nothing particularly exciting going on because of the fact that there are no repeats in the pattern. So we never have to worry. Every time that we detect a mismatch, if we detect a mismatch at D, well, we're going to start again in our pattern. If we detect a mismatch at C, well, we'll start again at the pattern. If we detect a mismatch at B, we'll start again at the start of the pattern. Same with A. There are no special links in our finite state automata, and so we can build the transition table right here very easily. All of the states go back to 0 except our special one at the beginning, -1, and this -1 is going to be just an implementation quirk. In terms of the actual finite state automata, there's nothing special about the fact that we put a -1 in there. It's just a marker to let us know that we're at the beginning. Now we have a slightly different pattern string. You'll notice that there is an overlap between the start of the pattern string here and another location in the pattern string there. That means, so we can move S up to that point and skip it, and move our pattern along, and start again. Now we have a mismatch, so we shift along once more. And we found our match. Okay, give me a moment.
If we now start moving C along, we'll match all the remaining characters and find the pattern. Great, not much change in this example, but now we'll tweak our target string slightly. Our target string is now ABC, AD, CAB, CABD. Same pattern as before though. Speeding through our initial steps, let's get to the point where S equals 0, C equals 3, and we're examining the second A in the pattern. This matches, so we increment C to 4, but now we have a mismatch. Let's see what happens if we skip S all 4 places forward. Well, if we skip 4 places forward, we'll skip over another possible starting position for our pattern match, S equals 3, where there's a letter A, just like the start of our pattern. So the maximum number of places we can skip is 3. Let's shake it up and change our target string again. ABC, 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 ABD. Now we successfully match at C equals 4, but have a mismatch at C equals 5. How many places can we skip S forward? We certainly can't skip 5 places. That would skip over both the A and B in the target string, which could be the beginning of a match. We can, however, skip 3 places. What's the relationship between the number of places I can skip S, the number of characters I've matched so far, and the size of the prefix, AB in this case, that's repeated here? If we keep following the pattern, we'll find that the number of places we can skip is the maximum we could skip if there were no repeats, minus the length of the prefix that's just been repeated. This gives us our rules that we can use to build our finite state machine. At each character, we have 2 transitions, one for a match and one for a mismatch. For a mismatch, add a transition back to the end of the longest prefix from the start of the pattern that matches the repeated segment inside the pattern. Once our table is built, to use it in the algorithm, we adhere to the following rule. On a mismatch, set C equal to the value in the transition table, e.g., set it back to the end of where the longest matching prefix occurred earlier in the pattern. Skip S forward equal to the difference between the old value of C and the new value of C. And that's it. Now that the conceptual hard work is out of the way, we're ready to examine the code, starting with the function that builds up our transition table. We have a loop that iterates through each position of the table S up to the length of the pattern M. You'll note that we start S at 2, pre-filling the first 2 entries with -1 and 0. The -1 we save for our transition from the start node to itself. The 0 for the first character we can also set because the first character is not a duplicate of any prior character in the pattern, precisely because it's the first character. So on a mismatch, we'll always go back to the very start. To fill the rest of our entries, we set C initially to 0, and we think as follows. what was the last character that matched successfully before the mismatch, i.e. at s-1? Now, does that character match the cth character of the pattern? The first time we do this, c will be 0, so we'll be comparing to the very first character of the pattern. If it does match, increment c, because when we move to the next s, we'll want to see if the prefix extends an additional character. Also, store the value of c in the transition table. This tells us how much we'll have to subtract from our maximum skip back over in the main KMP function. Okay, that's the first case. If the last character before the mismatch doesn't match the prefix, we check if c is larger than 0. That is there a place in the pattern where we could match an even earlier prefix of the pattern? If there is, we can use the transition table to find it and set c to that value. We then go back to the top of the loop and again test if we can match the prefix. Otherwise, if we're not currently at a prefix and if there isn't an early one indicated by a transition table, we can skip the maximum number of letters possible and reset c to 0. So we store a 0 in the transition table and move to the next index. We've built our transition table, and that's the hard part done with. Now for search itself. For each position S where the pattern could match, sequentially go through the pattern and stop when you hit a mismatch. When you hit a mismatch, set C according to the transition table and move S forward by the difference between the old value of C and the new value of C. There's also a trick here. If failure I equals -1, we just move to the next character in the target string and begin our comparison and set C to 0. And that's it for KMP. We'll turn now to a worst case analysis of the runtime of KMP. We'll approach this in 2 steps. The pre-processing, which really only has to run once for as many searches as we want, and then the search phase, to see which dominates if we are only performing one search. First, we'll start with the pre-processing analysis, or building the state transition table. Our table is going to have one entry for each of the indices to tell us what to do if we need to backtrack. By default, we'll only have one comparison that we need to do for each location, except if we mismatch, and there's a prior place to go to other than the start, so if there's another match earlier on that we could jump back to. This implies, however, that we already had done at least one prior match before this particular mismatch. Therefore, for each backtracking mismatch, there must be a match. So we can pair them together, and if we add them up, we'll get a maximum of 2m comparisons, assuming that at each time we've matched once and then had to do the backtrack. We're now ready to do an analysis of the runtime of the search component of the KMP algorithm. There are a maximum of n-m positions at which we could possibly find our match, and we're going to be tracking this using the variable s. At each place, we're going to do our comparisons using the variable c across the pattern, and sometimes we're going to have to backtrack it. But every time we do this backtrack, we're going to move s forward by the same amount that we backtracked c. So we can pair each backwards move of c with a forwards move for s, and this can happen a maximum of n-m times, which is bounded by n. So we know that we're going to have these pairs occurring a maximum of n times, and so if we count up the number of total comparisons, we get 2 times n. Don't forget though, if we finally do match on the last location, we're going to do a full comparison from with c starting at 0 going all the way to m. So we add it all up together, we get 2n plus m for our total number of operations. This gives us a runtime for the search component of big O of n, and as the search is going to dominate the pattern construction because n is bigger than m, we have our final runtime for KMP, which is big O of n.
We now have a fairly fancy technique to search for patterns in strings that's O of n average case. But can we use this to build a search engine for all the text in the value library? And this is an open question. I'll give it to you guys. Why or why not? Why can we do it? And if so, why or why not? Would KMP be a good choice to search through the text of all the books in the value library when you type in library search? Oh, Liam. Okay, let's have a chat.
alles digitized totally cool.
Yeah. So
Okay.
let's say all the books are in digital form.
So you have to do a list of all the books and then go through array of all the books and open everything array and search them through every single array.
So instead of putting them in an array, I'm going to be really stupid and I'm just going to shove all the letters in the book to the same place. Liam, and let's come around here a little. No, keep the microphone.
Oh.
Yeah, so instead of having your one array for every book, we're going to have one array with all the text for all the books. Do you think this is going to be a good algorithm for searching through all that text?
No, because I'm not sure if this is correct, but similar to the binary search, it's better if you start in the middle rather than just starting at the start because it's less likely to appear there.
Well, would we be able to rule out one of the sides? Do we know which side our pattern is going to be in? So if
No.
I'm searching for the word
No.
Harry in all the text of all the books, and we've split it halfway, do I know where the word Harry is in the
No,
left half and the right?
yeah.
So binary search isn't going to work. I mean, will KMP work?
It works. Take very long.
Why will it take really long?
Because I'll go through all of the text that from the start.
Yeah.
It might not be your text for one, it might not be very close to some. So
What did we just say the runtime of KMP was? Average case?
Big off.
You go to the
Yeah.
Yeah, big O of
Yeah.
n. And so how large is our n for every book in the value?
Gotta go with it.
Well, take a guess. How many characters do you think it is?
Couple billion.
Let's do the calculation and see.
Yeah.
We can hand that back to Liam. This is some text I extracted from the website of the Value Library today. There are approximately 78 kilometers of shelving filled with books in the Value Library, or in its storage at least. We can make a quick calculation to see how many characters that gives us. 100 pages is 10 millimeters or so. There are 300 words on a page, 5 characters in a word, which gives us 1,500 characters for every 300 words, which is like 150,000 characters for every 10 millimeters, which gives us about 1 trillion characters in the Value library. That's a lot of characters. Well, what do you think a good guess is for how long it would take to search through 1 trillion characters using a modern computer? Any guesses?
1 million years.
1 million years? Probably a little long. Have you ever tried getting your computer to search through a list of 100 items?
Yeah, probably takes a million seconds.
Seconds, do we say? Are we talking about seconds, days, years, hours?
Days?
Days, hours, okay, let's see. It's about 10 seconds for each search. But this relies on taking up an entire computer that has the database of the Value Library loaded in, and there probably aren't going to be that many computers that have loaded up with every single book. So
Wouldn't that also be linked to the speed of the computer?
it is linked to the speed of the computer. I said a modern computer, more or less. These numbers are kind of fudged anyway. I don't actually know how many characters there are in the Value Library or which computer it's running on, but about 10 seconds for a single search seems about right. Now, when you type in a search into the Value Library website, does it normally take 10 seconds? No, it takes far less than that. And this is just for one person making a search. So if you can imagine the entire university full of people, even if only 10 people are making searches at a time, you'd need 10 computers just to handle those 10 people. So it doesn't look like KMP is going to be a very good choice. O of n isn't really fast enough for this case. In fact, what we would really like is something that's proportional more closely to the pattern than it is to the size of the overall string. Maybe there's a way we can do this. If you remember this from my very first week, this is our icon for our time-space trade-off. So potentially we can make a trade-off using up some extra memory inside those computers running the searches in return for optimizing the amount of time that it takes to do a search. There are a number of other places where you'd want to do this. The Value Library isn't the only place where we'd want to do search through a really large amount of text. There's something you guys do every single day, I can promise you, which is search Google. If we think about the number of characters in the Value, well, it's a couple trillion. If we think about the number of characters on the internet, you're getting to a whole different class of letters. And so obviously an O of n algorithm is not going to work, and we're going to have to start relying on these trade-offs. Using extra hard drive space and extra space in our computer's RAM in return for reducing the complexity of the amount of time that it takes to run our algorithms. So we've got another demo that will help illustrate how we do this. I'm just going to I'm not going to tear it in two again, but I do need a volunteer who will help me out. And Ewan over there with the laptop that's got the red tinge on it and all the stickers. Yeah. Come on down. It's an easy one.
Come on down.
So I don't remember your name either, so you'll have to remind me. Ashley, okay. I'm not sure you've been down before. No. Okay, so here is the yellow pages. I want you to find me a bakery. So what's your current strategy for finding a bakery?
Randomly.
Probably not going to work. What about if we turn to the beginning of the yellow pages? What is there at the beginning?
Index.
Say it into the microphone. You've got to hold it right up to your mouth.
An index.
Okay, and how does an index work? Explain it to me as if I've never seen an index before. With the microphone again.
It shows alphabetically what you have in the book.
So what are these different things? Are these
Categories.
categories? Okay, so for each category, it gives us a... What's next to each category?
Page.
A page number. So we're doing the same kind of optimization here, aren't we? So you could very quickly, let's say, can you find me a bakery now?
Yeah.
Found one?
Let's see, is it showing?
Oh, you're on the right page. We'll leave it at that. There's some beautiful bakery here just waiting to be discovered. Anyway, why don't you explain to me your strategy for finding the bakery using the index?
Bakery starts with B.
Bakery starts with B.
You go to the page of the index that says bakery.
Yeah, so we looked at the index and we could jump directly to the right page. Do you think this was more efficient than the thing that we were doing where we were tearing out half the book and half the book and half the book?
Yeah.
Yeah, so why was it faster?
Because you know exactly where you're searching.
Yeah, we can jump exactly to the right page as soon as we find what we're looking for in the index. Thank you very much, Ashley. Can we have a round of applause for her for showing us how to use the index? This is the idea that we're going to use for our trade-off in certain types of searches. We're going to index data using shortened keywords or categories or shortened listing that will enable us to jump right to where we want to go. Now, obviously, we might have to do a little bit of looking through the index at the start and maybe a little bit of looking through the place that it takes us to at the end, but it's going to save us the big task of dividing the thing up and figuring out where it is, or sorting everything in the middle and sorting every single item every time we want to do a search. There are going to be efficiencies that we get out of this indexing. We can think of this for a few different real-world, instances. For the yellow pages, we can quickly find a category in the list of all the categories by looking at our long list of categories and then doing a binary search over the categories. So if the thing we're looking for is a bakery, we can look at roughly halfway down the list of categories and see, oh, a bakery before or after this category? Oh, it's before. Okay, we'll ignore the other half and go up the sorted list of categories and look halfway again. Oh, is bakery before or after this? Okay, well, it's going to be in one of the categories higher than this. The same kind of thing, except now instead of binary searching through the entire yellow pages, we're doing it just on a shortened list that condenses everything else in the book. We could also do this for a book index. You'll see many books that have more sophisticated language or difficult concepts like There used to exist these things called encyclopedias before Wikipedia was around, and you'd go to the back, and if you wanted to know where a topic was, you'd have these books that would just be indexes, and tell you where you can find a given word or a given entry in the encyclopedia. So we can do this for words as well. Now our question that's going to occupy the next few minutes and then the start of our lecture after the break is, can we make this work for patterns? This would be, for every character in a pattern, can we build an index? Now, of course, we've already seen this. Does anyone remember what this is called?
Been a long time ago.
It was a long time. It was the first week. Yeah. This is a very, very close. This is a suffix array. Now, the idea here is that we can store a list of all the different substrings that exist in our target. Then we can sort the list of suffixes. We can sort the list of suffixes, and then by jumping to partway through the list of suffixes, we can perform a binary search the same way as we did before, because now these are sorted, and look to see if a given suffix exists within the overall string. Now, of course, this could be repurposed for patterns as well. Can anyone see how? If I'm looking for a particular pattern and not for a whole suffix, okay, Liam, I need the mic again.
Here's the microphone.
Sorry, I'm going to take it down back to someone. Okay. You two have escaped thus far. Yeah. What was your name? Samuel. Okay. Samuel, so if I want to find the suffix cells shells in the string, how would I go about doing that? Hold the microphone right up to your mouth so everyone can hear. Yeah, cells shells.
Not sure.
Well, is it in our list of suffixes somewhere?
Oh yeah.
Yeah, it is, and they're ordered alphabetically, right?
Yeah.
Right, we see E at the top, L's, 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 cells, there we are, cell shells.
Yeah.
So we do have an algorithm that can search on sorted lists of things, don't we? Starts with a B.
Binary search.
Yeah, binary search. So we can jump halfway through and know if we look at L's, well, the string that we're looking for, cells shells, starts with an S. S is after L, so we can throw out the whole top half and just look in the second half. And if we recursively do this, we'll get to cells shells. Now, that helps us search for a suffix, but what if I just want to search for the substring cells and not for cell shells? Is there a way I can do this?
I'm not sure.
Well, what did I just find 2 seconds ago with you? What? Yeah?
Cell shells.
Cell shells. And is the string cells inside cell shells?
Oh yes.
Yeah. So if I want to check if the substring cells is in there, if I find cell shells, can I use that to check if I found cells?
Oh yeah.
Yeah, so why don't you explain to me how I do that?
I'm not sure.
I've given you most of the ingredients, you just have to put them together. So let's start at the beginning. I want to find if cells is in the pattern. So what's the first thing I do? You said it before, it started with a B.
Binary search.
Yeah, we do binary search and we see if the first letter is in there. Right? And
Okay.
if we've found stuff that begins with the first letter, now what do we do? So now we're at the part of the array with the S's.
And then start with the second.
Well,
character.
we can just repeat our binary search until we find the next letter along, which is the E, and keep going on and keep going on. Only this time, we don't look all the way to the end of the string, we just stop as soon as we get to cells. Searching for cells is actually a little easier than searching for cells shells, because we only have to check the first M characters where M is the length of our pattern. Make sense to you?
Yeah.
Get in there. Thanks very much, Samuel. Yeah, we can have a round of applause. We will learn how to analyze the construction of this table, the sorting, the building of it, the sorting of it, and the searching of it after break. But for now, the most important thing, more than even in doing some algorithms and getting your assignment done, take a little break, get some rest. We've had a difficult semester thus far. The only thing I want you to do, remember, algorithms are fun. Have a wonderful week off, and I will see you after the break.